As I mentioned in the first part of this 4-part video series on Prufer codes, we're attempting to show that the number of distinct labeled trees of order n is n to the n minus 2. And we're doing this by establishing a bijective correspondence between these distinct labeled trees and the number of sequences of length n minus 2 from the set of integers 1 through n. We do this with two algorithms. We need a way to take a labeled tree and produce one of these sequences, as well as a way to take one of these sequences and produce a distinct a labeled tree. So this is how Prufer did this. This is how Prufer proved this result of Cayley's. And we'll start with this algorithm 3.21. So this one is to construct the Prufer code of a labeled tree with vertex set 1 through n. So we need to be given an integer, at least 3, and a tree that's been labeled with those integers. We could also just say that has vertex set 1 through n. That's another way to say it's a labeled tree. And what we'll get out of this is a sequence of integers from the same vertex set. We allow repetition here. And we call this the Prufer code of the tree. So we're constructing a Prufer code for a given labeled tree. So here in this example, this is going to be our tree that will produce the Prufer code of. So this algorithm starts, right? And any algorithm is a step-by-step process. It takes the input and produces the output. We start with this loop. So this is a loop. It's a for loop in particular, if you're familiar with programming. For each integer I between 1 and n minus 2, we're going to perform the following task. And we'll keep doing this for each I between 1 and n minus 2. And then we'll finally have this sequence as an output. Okay, so how does this algorithm work? Well, if you're good at reading algorithms, you should be able to probably do this on your own right now. You can follow the algorithm, but I'm going to walk through an example of how we do this. So for each I between 1 and n minus 2, here my n is equal to, 8? So I have a labeled tree of order 8, labeled appropriately. And so we're starting with I equal 1. So this is T1 is my given tree. And what we'll do is we'll find the smallest leaf of the tree. So that is the leaf with the smallest label, and record its neighbor. Since it's a leaf, it only has one neighbor, so that's fine. And then we'll record that label, and then we'll remove that leaf from the tree and produce a new tree, which we'll call T2. So here, look at all the leaves. I have 1, 2, 3, 4 leaves of this. The one with the smallest label is 3, this guy. And so I'm going to record 3. So this is telling me A1 is equal to 3. I'm recording that. And then I'm going to delete this leaf from the tree to produce T2. So T2 is just going to look like T1, but with that leaf removed. And I keep the labeling 4, 8, 5, 2, 7, 1, 6. So now I have a tree of order 7, and I perform the same process now with I equal to 2. But again, I will look for the smallest leaf. So leaf of smallest label, again, I now have 3 leaves. The one with the smallest label is 4. So I've already messed this up a little bit. I always mess this up, so it's good to point this out. You don't record the leaf, but rather the label of the neighbor of the leaf. So actually A sub 1 is 1, and then I delete the leaf. All right, sorry about that, but that's an important thing to go over. You don't record the label of the leaf, but rather the neighbor of the leaf. And then we go again. So now the smallest label is 4. Here it was 3. The smallest label of a leaf is 4. And I will do the same thing. Now it's a sub 2. I will record the neighbor of this leaf, that's 8, and then produce T3 by deleting this leaf from the tree. Eight, 5, 1, 6, 2, 7. Cool. So now I'll repeat the same process. Find the leaf with the smallest label, this time it's 6, and record the neighbor of that leaf. It's 1, and delete that leaf and move on to the next tree. So T sub 4, I delete that leaf, and I'm left with this tree of order 5. So 1, 5, 8, 2, 7. So now my smallest leaf is 1, its neighbor is 5, so A4 is equal to 5. And we continue on. Now I'm just left with this path, 7, 2, 5, 8. And I repeat the process. Now the smallest leaf is 7, its neighbor is 2, so I will record 2. And produce the tree T6. 2, 5, 8. Smallest leaf now is 2, its neighbor is 5, so A sub 6 is equal to 5. And right, so I repeat this process for I between 1 and n minus 2. So let's see, I've done this now. I have A sub 6. Remember, my original tree had order 8. And so now I'm done. I will just make a note of the sequence, the Prufer code. Now we have the Prufer code. It goes 1, 8, 1, 5, 2, 5. 1, 8, 1, 5, 2, 5. Notice this is an ordered set, right? It's a sequence. So you should use parentheses for these codes. And this is the Prufer code for that given tree. So you can do this for any labeled tree. And if the labelings are distinct, well, I guess we have to show that you'll get distinct Prufer codes, but more on that as we go through the video. All right. In the next video, we'll analyze the algorithm and look at an example of the algorithm that takes a given sequence. Like, so how can we go backwards now? How can I take a sequence and then produce a labeled tree from that sequence who's such that that tree has this as its Prufer code? That's what the next algorithm is going to do.